In just a few short millennia, a volcanic force can drown an area the size of France in molten rock, unleashing chaos powerful enough to wipe out dinosaurs and poison the air across continents. Yet, it is these very eruptions, the birthplaces of new islands, that allowed mammals, our ancestors, to rise. If such devastation remains possible today, what triggers the next wave of planetary upheaval? Lava from a single volcanic event can cover more than 100,000 square kilometers, an area as vast as France. These outpourings, known as Largest Igneous Provinces, are not slow dribbles but continent-scale floods, sometimes erupting in pulses that last less than 5 million years. Imagine a landscape where, in a geologic blink, rivers, forests, and entire regions are buried beneath a sea of molten rock. The Ontong Java Plateau, for example, stretches across an area one-third the size of Australia, its basalt layers stacked deep beneath the ocean. In the United States, the Columbia River Basalt Group blankets over 200,000 square kilometers of the Pacific Northwest, shaping canyons and cliffs that still dominate the region today. These eruptions dwarf anything seen in recorded history, their footprints visible from space and their legacy etched into the very crust of the planet. Deep beneath the planet's surface, immense forces are at work. The largest lava floods begin far below the crust, where hot, buoyant mantle plumes rise from depths over 2,000 kilometers. These plumes carry heat and molten rock upward, pressing against the rigid plates above. When a plume head reaches the base of the lithosphere, it spreads out, thinning and cracking the overlying crust. In some cases, this process combines with continental rifting, where tectonic plates pull apart, creating fractures that act as escape routes for magma. The result is a sudden release of enormous volumes of basaltic lava through fissures that can stretch hundreds of kilometers. Unlike typical volcanoes, these eruptions are not tied to plate boundaries or subduction zones. Instead, they represent a direct pipeline from the deep mantle, unleashing energy stored for millions of years in a matter of months or centuries. This geodynamic engine is the true source behind the world's largest volcanic provinces. 66 million years ago, the Deccan Traps in India erupted with a force that defies imagination. Layer after layer of basalt buried the land, each pulse of lava releasing clouds of carbon dioxide and sulfur that drifted across the globe. In the rock record, a sudden drop in carbon isotope values, known as a delta 13C shift, signals a world in turmoil. Forests and oceans suffered, and non-avian dinosaurs vanished from the fossil record. Yet just above the final flows, new fossils appear. Small, furry mammals, once overshadowed, began to thrive in the aftermath, seizing the empty niches left behind. From devastation, evolution found a foothold. Across the Pacific Northwest, the Columbia River Basalt Group stands as a testament to the scale of volcanic flooding. Between 17 million and 6 million years ago, eruptions poured out more than 174,000 cubic kilometers of basalt, forming layered cliffs and deep canyons that still shape the landscape today. In stark contrast, Germany's Eifel region witnessed the violent birth of Locher See just 12,900 years ago. This eruption blasted ash across Europe, its tephra found as far as Sweden and Italy. Both sites reveal how volcanic forces can transform entire regions, sometimes over millions of years, sometimes within a single human lifetime. When volcanic provinces erupt, the atmosphere and oceans become battlegrounds for chemical chaos. Sulfur dioxide rises high into the stratosphere, forming sulfate aerosols that scatter sunlight and trigger years of global cooling. Crops fail, ecosystems falter, and sunlight dims. But the story doesn't end there. As the haze clears, carbon dioxide lingers for millennia, trapping heat and driving a relentless greenhouse effect. Oceans absorb much of this carbon, growing more acidic and losing oxygen, which suffocates marine life. These twin forces, brief cooling from aerosols, then long-term warming from carbon dioxide, create a climate whiplash that stresses life on land and in the sea. On Iceland's Reykjanes Peninsula, a network of seismic stations hums with constant data. Every tremor, whether deep underground or just beneath the surface, is tracked in real time. Seismic swarms, sometimes hundreds of tiny quakes in a single day, signal magma shifting below. Scientists compare patterns, looking for clusters that reveal magma rising or spreading sideways. Satellite radar called InSAR measures ground movement down to the millimeter. Even a subtle uplift, just a few centimeters, can warn of magma collecting beneath the crust. Together, these tools give volcanologists a live feed of Iceland's restless underground, turning raw data into early warnings for the communities above. Volcano monitoring agencies treat these regions as low probability, high consequence hazards. Multi-gas stations track shifts in sulfur dioxide and carbon dioxide, searching for the telltale ratios that hint at magma on the move. Communication strategies are practiced and refined, so that if danger rises, warnings reach everyone in time. The message is clear: vigilance matters. Even rare events demand attention, because the risks, though unlikely, can reshape entire landscapes and lives. Large igneous provinces still simmer beneath our continents and oceans. Their next eruption could reshape life on Earth again, reminding us that our world's stability is only ever temporary.